Okay, I want to talk about perception and mental models. And there's a couple reasons why I want to talk about this. The first one is that later in the semester, we're going to be dealing with machine learning. And when we do this, we're going to be working with images and how the computer learns to perceive things about images. And its model of perception is not like human beings. If you give the computer this picture, it is going to say that is probably something more likely to be a tree than a person. Now, when we look at this, and this is taken from the mini-series Dune on the Sci-Fi Channel, it's a single frame from that. It's the Lady Jessica looking out the window, but I don't think any of us have a difficulty in perceiving that that is actually a person. Even though it is green. She's not green, we know that, but we compensate for the errors in lighting in our brain automatically. At least most of us do. Okay, and I'm going to talk about this in terms of the fact that what you perceive is not reality. What you perceive is a mental model that you have created. And when we generally, as a group of people, agree on what that mental model is, that oranges are orange, that these things, that this thing that looks like this is a person, that group agreement is what we use as the model in our heads, this group hallucination for what reality is. And inside your skull, your brain has no direct connection. It just has things that feed in information, and it processes that information in beautiful, amazing ways, but sometimes not correctly. And we're going to poke at some of the not correctness as we look at why I say it's just a group hallucination that we're having that is our mental model. Now, the second reason why I want to look at this is because we're going to be talking about models inside the program that you have to develop in your mind, the ability to look at a piece of code and build this mental model of what it's doing inside the computer. And that model is a long ways away from what's really going on in the computer. I mean, let's be serious. Down inside the computer, everything that's going on is just an electrical signal that is either on or off. Okay, that's it. There's nothing else happening inside there. And we know this from some amazing mathematical proofs done by Alan Turing, that everything we do from computers, that's all it is down at the bottom, it's either on or off. And it has no greater perception of the universe than just a bunch of signals that are on or off. So the computer has no mental model either. It has to, if we are using some sort of machine learning, we're going to teach it to do things. And it will be creative not because it is a creative device, but because it's going to give us answers sometimes that are completely bizarre. Because when we train it on some particular thing as machine learning, its entire universe is the training set. That's all it knows. And if you allow that training set to have extraneous things in it, and I'm going to show you some examples of some extraneous things, then its conclusions about the nature of what it is going to be vastly different than us. Because our mental model of the universe includes this vast array of experiences that we've had in the entire world, whereas its mental model is the training set that we gave it for a particular task. And those two are hugely different. So we're going to look at pictures like this again later in the class, but I want to show you some other optical illusions as I try to develop in you an understanding of what you actually perceive. The first one has to do with color. Which square is darker, A or B? And if you're a normal human being, then you will perceive B as definitely lighter than A. But if we put a background around it that shows that instead of the shadow from the green thing, they look like they're the same darkness. And when a computer perceives these things, it sees them as the same darkness. When you perceive it, your brain adds in the fact that, well, it's in a shadow and therefore it must be lighter, and it gives you bad information, basically, as to what is really there, as opposed to giving you information on the perception of the model of the world. So your model of the world is not the same as what's actually out there. Now, I'm going to show you another example of this same illusion that's done, this is, a computer thing. Did I somehow cheat? The next one is done as an actual person. It comes from YouTube, not the original research. This original research came from MIT. But here's a little snippet from a YouTube video where it's done in the actual real world with lighting and shadows, and somebody has actually built this in the real world. I've got the YouTube user up there that on this video, so you can go hunt it down if you want to go see it. And here's an actual person coming in. Not a fake person, this is a real person, and this has actually been done. So you can see that this is not some cheating process for colors. Now here we've got the squares, and they're actually movable. She's going to reach out and pick up that square, yes, okay, and move it over, and guess what? It's exactly the same color. So she's actually going to pick this up and put it back so that you can see that it works in the opposite direction too. And your brain corrects it. Now here's one having to do with color instead of shades. And the brown square on the top is actually the same as the bright orange square on the side. And your brain tells you that they're different, but if we make them dark, if we decontrast the rest of it, yeah, now let's put it back, and guess what? We go back to your brain telling you that they're actually different. So, our first couple of examples were basically visual examples. But is this only a visual problem, or does it extend beyond just the visual? Two things I'd point out. First of all, you know butterflies? Okay? Butterflies see in 5 color spectrums. So they have a completely different perception. Dogs see in 2. Mantis shrimp see in 15 visual perspectives. So us human beings only see in 3. So that's part of it. We're not seeing the whole spectrum. We're seeing a little piece of it that seems to be useful to us. In fact, human beings see about 3 times as much green as any other color. Okay, we really like green. So one of those things that you find out is that some kinds of video compression actually throw away a bunch of the red and blue because humans basically like to see different colors of shades of green. So there is that kind of information, but it also happens in the audio. So I'm going to give you an example of an audio, and you get a choice of pick 2 words off the left or off the right and look at those and see if you hear the same thing. You can replay this, so you get the opportunity of going back and doing it and listening to it over and over again and try it with different things and see if I'm telling you something else. But look at it as in the audio perspective and see if you can see that there are audio examples as well. Now I'm going to put up something on the screen that says either brainstorm or green needle. And you need to focus on one of those 2 things and listen and see if your brain fills it in. Try it multiple times, switch back and forth. See if your brain is filling in the missing pieces based on what you're seeing, not what you're hearing. Once again, I've built a little tiny program that I'm going to run in the visualization tool. And when I talk about it visualizing, what it does is this tool builds a visualization of what I think about when I code. And I've done a list. A list is a collection of different values. And the first line, when it runs this, creates the list. Note the subscripts. Subscript 0 is 5, subscript 1. That means we could get to the individual things. But when I think about a list and I see it, I see some ordered set of data that looks something like this. Now, if I go to the next line, it's going to print it out. And up here I have a printout. And when I look at a printout, I say, well, what is the values that it's going to print out? How is it going to substitute? And what is it going to look like? And you'll notice that I've used a function append that says on this list append 18. And now we have an 18 at the end. And I append a 9. And then I print it again. But the key piece here is that this is not what's inside the computer. The insides of the computer is a bunch of wires and electrical and transfer of data from memory to a computational unit, do some computation, move it back. This is what's going on inside the computer. But what I visualize in my head for what happens in the program is something like what you're seeing in this visualization. When you learn to program, this is what you're learning. You're learning to be able to communicate to this collection of electrical circuits in some sort of a language, and you're using your ability to visualize to be able to project your visualization into a piece of code that gives you the common ground to communicate between you, the human, and the computer. And your ability to visualize and see this and think through it is what determines your skill at programming. It's how you perceive this, and you create this model in your head, just like the model outside you that isn't really the world, but this is your model of the world. And you use your ability to hallucinate this magical model of what's in the computer, and you use that model to say, did it do the right thing? Did it do the wrong thing? Is it producing what I'm expecting? That's the debugging process. And that match between what you expect and your mental model and what it does is what you're after. And that's what we're trying to build as in developing the process of programming.